So, good evening. Today I'll be discussing about the week 8, the problem solving and doubt clearing session. So, in this session, I'll be talking about this number systems. I'll be going through it again. Also, regarding Q format, also I'll be talking about how we do multiplication and when this Q format, also how to what changes happen, etc. Then I'll discuss about digital voltage mode control, the Verilog code, the code for digital PID controller. Also, I will show the hardware results and the code for mixed signal current mode control also will be shown. Also, we will discuss about pulse skipping modulation. So from last week, does anyone have any query? Okay. If you don't have, I'll proceed. So we'll be starting with number systems. We also discussed about this last time also that numbers can be binary, hexadecimal. They can be decimal or they could be an octal representation. But here we will be mainly consider about binary and decimal. And in binary also, there we have, it can either be signed or unsigned. So straight binary is unsigned, can only take positive values. But 2s complement and offset binary, they are signed representations of binary numbers, and they can take positive as well as negative values they can take. Okay. So let us consider this case. This is for 3-bit, okay, for 3-bit representation. Based on these bits, we can get straight binary will be of this form. 2s complement will be 0, 1, 2, 3. And when it is 2s complement, the range will be from -4 to +3. Okay. Similarly, for offset binary, the range will be -4 to +3. And we know how to convert this straight binary to 2s complement. So what you must do is, suppose you have 4. Okay. You want to, suppose you have a number in 1s complement, you want to find its 2s complement. So you will invert it. You will first take its 1s complement and then you will add 1 to it. So that's similar procedures for, and for offset binary, what we have to do is, we have, let us say, this 101. Okay. This is representing -3 in 2s complement. Okay. 101 is representing -3 in 2s complement. If you want to convert into offset binary, what do we have to do is just the MSB, we have to change it. Flip the sign of the MSB, it becomes 001, and this will become -3 in offset binary. Okay. And this is for 2s complement. So we need 2s complement because our ADC's output is in the 2s complement form. And we require offset binary because the DAC's input, this has to be given in the form of offset binary. Our ADC is a 10-bit ADC and our DAC is a 12-bit DAC. Okay. So, Rajesh, do you have any doubts in this? Any queries in this?
No.
Okay.
No, sir.
So I'll proceed. So we talked about Q format, where it is just like a notional concept. It is what we are doing is Q format we are applying for signed numbers, and we discussed it. Suppose it was, we'll just take our own example. Q 3.2, okay. So it will have, assume we take this number 11011. So it will be, there will be a 3 here. So this 3, there's a dot and 2. And this will be 2 raised to 0. This will be 2 raised to 1. This will be -2 raised to 2. This will be 2 raised to -1. This will be 2 raised to -2. So the value which I will get is
6.75.
Okay. How much? Sorry, how much?
6.75.
No. Because it is signed. Okay, so 1 into minus 4 should be minus 4 plus 2 plus 0 plus 0.25 plus no, sorry, plus 0.5 plus 0.25. So you will get it to be 2.75 minus 4. That comes out to be minus 1.25. Okay, it comes out to be minus 1.25. Okay. So you must remember in this format, let me just again write Q3.2 110.11. So this is raised to 2 raised to minus 1. This is raised to 2 raised to minus 2. This is 2 raised to 0, 2 raised to 1. And this is minus of 2 raised to 2. So this is my sign bit. Okay. This is my sign bit. This is what determines if it is a negative number or a positive number based on the value which is in the sign bit. Okay. So this Q format is for the 2s complement notation. So okay, I'll also show some examples also we will solve. So in that I will explain these things. Okay. Well, let me just again once more do. Assume we have Q 2.3. Okay. This is same over here, Q 2.3. So it will have, this is my MSB. My MSB is over here, MSB is 0. That means the sign is, that means it is a positive number. What will happen over here? This is 2 raised to 0. This is 2 raised to minus 1. This is 2 raised to minus 2. This is 2 raised to minus 3. So the value which will come out over here will be 1.5. Like this 0.5. This is 0.25. This is 0.125. So it comes out to be around 1.875. Okay, it comes out to be 1.875. So this is the maximum value plus 1.875. But if you want to get the minimum value, which you will get, that will be, this is 2 raised to 1. Okay, minus of 2 raised to 1. So the minimum value is minus 2. Okay. Any queries in this? Okay. So over here, my MSB is my sign bit. Okay, my MSB is my sign bit. Now what happens is, if I'm doing Q1.4 plus Q2.3, see both are of 5 bits. Okay, both are of 5 bits. But this N and M are not equal. Okay, N and M are not equal. So when you add it, it would come out to be Q2.4. Okay, maximum of N1 and N2 and maximum of M1 and M2. Okay. So that also you must take care. When you do this, what first you have to do is this Q1.4, you have to convert it into Q2.4. Okay, let me go with the easier example. Let us say Q2.3. Okay, Q2.3. Q2.3, we have to convert it to Q2.4. So what we must do, we must add an LSB here. Okay, we must add an LSB. So suppose Q2.3 was some number. Okay, it was some, let us say 01.110. Okay. I want to convert it into Q2.4. This same number, it has a value of 1.75. Okay, I want to convert it into Q2.4. So in Q2.4, I will represent it as 1.1100. Okay, this also has a value of 1.75. So in this way, I am not making any change in the value. I'm just padding it by 0 in the LSB side. So this is when I want to change this part, when I want to change this. Now, let us consider Q1.4. Okay, Q1.4, let us assume was 1.0100. Okay, when you find its value, you will get its value to be minus 0.75. This is Q1.4 and its value in decimal will be minus 0.75. Why? Because this is minus 2 raised to 0 and this is 2 raised to minus 2. So its value comes out to be minus 1 plus 0.25 So that comes out to be minus 0.75. Now, the same number 1.0100, which is Q1.4, I have to convert it into Q2.4. So to convert this into Q2.4, what I will do is I have to make it Q2.4 and I must still retain the same value of minus 0.75. So do that, what I will do, this is my MSB, okay? This is my MSB. I will do what is known as a sign extension. Okay, I will do what is known as a sign extension. So what I will do is, I will retain these numbers as it is, and the sign of the MSB, I will add it over here. I will add it over here. So effectively what I'm doing, I'm changing the sign bit. The sign bit now becomes this. Now if you find the value of this representation, this will be 2 raised to 0. This will be minus of 2 raised to 1. And this will be 2 raised to minus 2. So the new value which I get will be minus 2 plus 1 plus 0.25. And when we do the sum, it will come back to be minus 0.75. So in this manner, when I changes Q1.4 to Q2.4, I'm going to just use the MSB and I'm just going to add those MSB. So that is known as a sign extension. When I'm converting Q2.3 to Q2.4, I'm adding an LSB and I'm just padding it by 0. Okay. So I hope till here there are no queries, or if you have any doubts, please ask, because we'll be using all this. Okay. All right. So any queries here?
Sir.
No. Okay. So that is there. Now, what will happen when I'm multiplying? Suppose I'm doing Q2.3 to Q1.4. Now, what the number will come out to be? It comes out to be Q of 2 plus 1 dot 3 plus 4. That is Q 3.7. But this has one sign bit. This also has one sign bit. So this Q3.7 will have around like 2 sign bits sort of. So we can ignore and make it Q2.7, which has only one sign bit. Okay. So over here it is told. Okay. So if I have Qn1.m1 cross Qn2.m2, it will be Qn.m, and my n will be n1 plus n2 minus 1, and my m will be m1 plus m2. Okay.
Sir, discarding this bit in the integer part, in the integral part, we have to discard the MSB bit, right?
In which part? In which part?
In you are saying you have to drop one bit,
Yeah. Yes.
n1 plus n2.
Yeah.
Is that the MSB or LSB of the integral part?
No, there's no integral part over here. For the n part, right? For the Qn1, right? You will be
Okay,
discarding the MSB. MSB you'll be discarding.
okay.
Okay. Yeah. Okay, so now let us consider a PI controller. So as you know, PI controller will do Kp plus Ki upon S. This is for continuous domain, okay? For continuous domain. In discrete domain, we use what is known as difference equations. Difference equations. So the part which corresponds to the proportional term will be equal to Kp into V error. Part which consists of the integral term, that is Ui of n, is Ki into V error plus Ui of n minus 1. So what I must take into account is my Kp may have it may have format Q 3.7. My Ki may have format Q 2.8. My V error may have format Q 1.9. Okay, these are the formats for these things. So they are all different. When I multiply Kp into V error, okay, Kp into V error, when I multiply, what will be the Q format which I will get? Yes. Yes, tell.
Sir, in all this KP, KI, and VRR,
Mhm.
the MSBs are the signed, right?
Yeah,
In
in
all this,
all
in the
these
integer part,
representations.
MSBs are okay.
Oh. Yes, in the integer part, the MSB is the signed bit. MSB is the first bit. Okay, that's the most significant bit. Okay, yeah, it is signed. Yes. So if I have this,
For if sir, if you try to equal the Q number,
okay,
then we will add one to the MSBs.
okay,
Not one. We will add whatever is there on the integer part. We will just add it on the MSB, so that the Q numbers Q n dot m will become equal for the, if we are trying to make equal two numbers of different Q value to be of
mm-hmm,
equal to be of equal Q, then
mm-hmm,
in the MSB part we will try to add one
mm-hmm.
or zero. It depends on the MSB there.
Yes, yes, correct, yes,
And then in the decimal part, we will try to add zero in the LSB.
yes. That is for we have to convert it. Convert it from one to one. Yes. Okay. So
In
actually,
decimal part it is equal, but in the
mm,
integer part, the MSB you are adding depends on the MSB already existing there, right,
yeah,
sir?
yeah, yes, correct.
Okay.
Yeah. So Madhu was asking something. What is the question? How signed? Okay. So this is a sign notation over here. Yes, let us assume this number Q2.3. Okay. This 1, 2, 3, 4, 5. Okay. So this can be some bit. It could be 0, 1. Assume 1. This could be 0. This could be 1, 1, 1, etc. So in this format, when we are told it is a sign bit, the first bit is my sign bit. And I have assumed a dot to be over here. This is just fictional. This is just for my understanding. This is not for the compiler to understand. It's for my understanding. So this value, I will write it as 2 raised to 0. This will be 2 raised to 1. But since it is a sign bit, this will be multiplied by minus 1. Okay. This will be 2 raised to minus 1. This will be 2 raised to minus 2. This will be 2 raised to minus 3. That is why this is a sign bit, because I can take values from the range of minus 2 to plus 1.875 using this method. See, normally the numbers are just integers. It can be 0, 1, 2, 3, 4. But what if I want to get it in this decimal format? So for that, we have to use this concept of Q format. Okay. And in that, since they are in 2S format, the MSB will be the sign bit, and hence we can get negative numbers as well as positive numbers.
Sir, here it is, in the example you have taken, it is -1, right, sir?
Well, in this example,
Yeah. The
the
lowest value that we can represent is -1, right?
no, minus 2, right? Because this is 2 raised to 0. See, if I want the lowest value, it will
Okay.
be 1, 0, 1, 1, no, 1, 0, 0, 0, 0. All will be 0 except the MSB. And this is raised to 2 raised to 1. So it is 2 into minus 1, so minus 2.
Okay.
And if I want the maximum positive value, it will be 0, 1, 2, 3, 4. And that if you do, it will come out to be plus 1.875. Okay. So what I wanted to say was, this is KP into V error. Okay, when I do the multiplication, the Q format which I will get will be, see, V error is Q1.9, KP is Q3.7. So when I do the multiplication, it will be 1 plus 3, 4, minus 1. So it will be around Q3 point, and this will be 7 plus 9. So 7 plus 9 will be 16. So the Q format will be Q3.16. Similarly, for KI, okay, for KI into V error, this KI into V error which I have will be KI is 2, V error is 1.
2.70.
So Q2.17. Okay, so each one has a different Q format. Now the overall output, the VCon, the output will be equal to the proportional term plus the UI of it. Okay. So I need to make them of the same format. So I have to make this effectively of Q3.17. So what I will do, the proportional term, I will pad a 0 at the LSB, and at the integral term, I will just sign extend the bit so that both will be of the form Q3.17. Once I make both of the form Q3.17, then I add them together. And once I add them together, I get vcon, which is of the format Q3.17. Okay. So we will also be having some sums also solved examples will be there. We will solve an sums. So there we will try to understand it in more detail. Okay.
Sir?
Yes, sir.
Sir, in multiplication in the Q format multiplication also, do we need to make these n and m equal in both the numbers?
No, suppose I'm multiplying A and B, right? The Q formats can be different. It can be Qn1 dot m1 and multiplied by Qn2 dot m2. Those can be different. But when I add it, if I'm adding A plus B, then I have to make sure that both should be of the same format. Okay.
Sir, then what about that if two Q formats are added, you will take the greatest value of n and m.
That was for multiplication. Okay, I'll again try.
No, multiplication.
One minute.
Multiplication we are adding now, sir. N1 plus N2.
Yes. 1 minute. I have A is Qn1 dot m1. I have B, that is Qn2 dot m2. First, I will talk about multiplication. So for multiplication, that will be A cross B, A to B. This Q format, the new resultant number which will come out in this form, Q of n1 plus n2 minus 1 dot m1 plus m2. Okay, this is for multiplication. In multiplication, it is not required that n1 should be equal to n2 or m1 should be equal to m2. That is not required. Okay, this is for multiplication. Multiplication A cross B. But if I want to add A plus B, then I'll need to make this of the form Qn dot m, B also of the form Qn dot m, and then the resultant A plus B will be of the form Qn dot m. So now what is my n? My n will be the maximum of n1 or an n2. Whichever of n1 and n2 is my maximum, that will be my n. And for m will be the maximum of m1 comma m2. Okay.
Yeah. Sure. If then there may be a chance when both A and B should be padded. There may be cases.
Yeah, there will be
cases.
Equal, yes. Yes. Okay. So I hope Madhu Kumar that answered your question. Okay, these all we should have done it last time itself, but last time it wasn't able to be done. So now I'll go to next part. Okay. So these are some questions. Okay, let us consider this question. I have a 10-bit ADC. Okay. So 10-bit ADC I have. Alright. So the Q format is 1.9. This is the default one which is being used in search hardware. Okay, this is the default one which is used in search hardware. So 10-bit ADC gives value Q1.9. So when they say 10-bit ADC, you must use of this format because that is the one which is being used in the course. Now I have KP. Okay, KP is in the form Q2.8. Q2.8 will be what? There'll be this big 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this entire thing. So there's a dot over here. and this will be 2 raised to 0. This will be 2 raised to 1, and because it is a sign bit, it will be minus 1. This will be 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, and so on. It will go on till it will be 2 raised to minus 8. Okay. Now this could be 1, this could be 0, like that. It can change. Okay, it can change. It can change. Now I want to find the maximum negative value. So if I want to find the maximum negative value, all these 2 raised to 0, 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, etc. They are all positive. They will, if they are 1, they will add. Okay, but I want to find the most negative thing. So if I want to find the most negative number, I must just do 1, 0, 0, 0. Everything else will be 0. Okay, everything else will be 0. Then the value I will get is minus 1 into 2 raised to 1. So this will correspond to minus 2. Okay, so in Q2.8 format, I will get a maximum value of minus 2. Now I want to find what could be my maximum positive value. So if I want to find the maximum positive value, what it will be, this will be 0. This will be 1, 1, 1, 1, 1, 1, 1, 1, 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. Okay. That would mean my value which will come out over here. See, this will be around value of 1. This will be 0.5, 0.25, 0.125. This will be 0.0625, etc. Like that, we keep on adding. So if you add that, let us see, it is actually geometric progression actually. Let us see. Does anyone know what is the formula? Okay. The formula for geometric progression actually is the sum is a into 1 minus r raised to n upon 1 minus r. Okay. So over here, n actually is 9. It is 1 into 1 minus 1 minus 0.5 raised to 9 upon 1 minus 0.5 is equal to 2 into 1 minus 0.5 raised to 9. That corresponds to how much? 0.5 raised to 9 to minus 1 plus 1 into 2. That corresponds to 1.996. Okay, it corresponds to 1.996. Okay. So yes, so have you guys understood, or this I have confused you guys?
Understood, sir.
Okay. So basically, minimum value or maximum value you have to find. Minimum value is simple minus 2, but for the maximum value, if the bits were increased, this value will tend to plus 2, but it will not be plus 2. Okay, that is the limitation. So this is the case. So the meeting will end in 1 minute. So then we'll again start the meeting. Okay, I'll just end this meeting and I'll start a new meeting. Okay, so that's how we did for the KP of Q2.8. Now let us consider for Q3.7. Okay. Okay, let us now what will be for Q3.7? If you will do for Q3.7, can anyone tell me what it will be for Q3.7? The maximum and minimum value.
Value is minus 8.
Minus 8. See, you should remember.
Yeah, minimum value is minus 8.
4. Minus 4.
Yes, it will be minus 4, right? Because assume this
And
is
the
like
maximum
this.
value is 3.99 something.
Yeah. So this is actually 2 raised to 0, 2 raised to 1, and minus of 2 raised to 2. Maximum value is minus 4, minimum value is minus 4, maximum value will be around 3 point something. Okay.
4, no, sir, minus 4.
Minimum is minus 4.
Sir,
Okay.
we'll put that 1 and 0.
Hmm.
Sir,
Yes,
sir,
yes,
if you
still.
put that 1 and 0, it will become 2 power 2 minus 2 into 2, 1 into 2 to the power 2.
Yeah, so minus 1 to the power 2 is 4, no?
3.7.
For attain maximum value.
Minus 12.
Are you talking about the minimum or
Yeah.
the maximum value?
Maximum negative value.
Maximum negative value is minus 4.
Minimum.
Sorry, maximum, the minimum value is minus 4. Hmm. The maximum value will be around some 3.99 something. Hmm. That way. So you just have to remember the concept that if I want a maximum value, my MSB will be 0, all other bits will be 1. Okay, all other bits will be 1. That is what you must, that's the goal of this. Okay. Hmm. So that is the way we are finding the maximum minimum values for KP and KI. Hmm. Now, okay, so now we will see what is the Q format of NCON. So what is NCON? After resizing, we must do proper resizing. So we have ADC is 10 bit. Okay. So my V output of my ADC will be in the form Q1.9. So my V error also is of the form Q1.9. Okay, this is the Q format of my V error. My KP is Q2.8. So the part corresponding to my proportional term is Q2 dot proportional term is KP into V error. That is Q2.8 into Q1.9. That is equal to Q2 plus 1, 3 minus 1. That is 2.8 plus 9. That is 17. So this is Q2.17. So the part corresponding to my proportional term is Q2.17. The part corresponding to my integral term is Ki into V error. Okay. Integral term is actually a huge thing. Integral term is actually ui of n is equal to ui of n minus 1 plus this part. Okay. Plus this part. Okay. Ui of n, the overall output of the integral term is ui of n is equal to the previous value plus this value. Okay. So I'm considering for this value. This integral part is ki into v error. So ki is q3.7 into q1.9. So the q format will be 3 plus 1, 4 minus 1, that is 3 dot 7 plus 9 is 16. So it is q3.16. Okay. So,
Sir,
yes,
here we are taking V out Q of V out to be Q1.9 since
yes,
it's a 10 bit.
10 bit ADC, yes.
But uh, how uh, how we are saying it is 1.8, it can be 2.8 also.
Which is 2.8?
This Q V out, Q format of V out.
Yes, yes. The ones which Sir has used in his code, it is Q1.9. Okay. So you
Okay.
also must use the same one. Just trying to keep it consistent. So
Okay.
is there any question or doubt in this part? This multiplication part? Okay. So now my PI controller's output. My PI controller's output is VCon. And my VCon is equal to proportional plus UI of N. Okay. Now the issue here is proportional is Q2.17. My UI of N is Q3.16. So they have to be converted. Okay. This has to make Q3.17. This also will be made Q3.17. So my VCon will be of the form Q3.17. Okay. Any queries in this? So let us go to the next thing. Now, this is KPA is in the form Q2.8 and its value is 1.90625. How will you get it in signed format? Okay, what will you get the binary representation of this? Earlier, what we had 1011 something Q2.3, and then we found out the value in decimal value we found. Now we have the decimal value 1.90625, and we want to find the binary representation of it. So first, let us see how to proceed with it. I've given a simple example. So Q2.8 is 1, 2, and this is my dot, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So this is raised to 2 raised to 0. This is minus 1 into 2 raised to 1. This is 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4, and so on, up to 2 raised to minus 8. Okay. Now, I want to find 1.90625. First of all, how you must look at it is a positive value. It is a positive value. So my MSB has to be 0. Okay, that's the first thing. MSB has to be 0. And before the decimal, again it is positive. Means again it is the decimal value is not 0. It is not 0 point something. It is 1 point something. That means this has to be 1. Okay, so this is 2 raised to 0 into 1. So this corresponds to 1. Now I want to find which and all bits are high. Okay, which and all bits are there. See, in the exam and all, there'll be MCQs. It is an MCQ thing. So you'll have multiple options, and you can, for each representation, it will be like around, like it will be 0, 1, 1, 1, 1, or 0, and 0, 1, 0, something, etc. All that could be there. And based on that, you have to, and then another example maybe 0, 1, 1, 0, 1, 0, 1, 1, 1. So you can find the decimal value corresponding to this, decimal value corresponding to this, and check which of them comes to be this value. Okay, that is one method. Another method is you can use like the binary algorithm. Okay, so now this is 1. Now you must check whether it is between, and this is corresponds to 0.5. Okay, so you check whether it's between 1 and 0.5. So this is 0.9. So this also has to be 1. Okay, this is 0.9. So this also has to be 1. So my new number which comes out from this, that is, these two are ones. Let us consider all others as 0. So the number which I get is 1.5. And my original number is 1.90625. So what is the difference of them? It will be around 0.40625. Any doubts till this?
Please repeat it once.
Okay. Let me not complicate it. It's actually, I'm complicating it for you guys. First, you understood why this is 1?
Yes, sir, it is clear.
Okay. Now, I want to check whether this should be 1 or 0. Okay. So I make this 1. Okay, I make it 1. So the value I get is 1.5. Yeah, value I get is 1.5. And this 1.5 is less than this 1.90625. That means so that means this is correct. Okay, that means this is correct. That means this bit has to be 1. Now I'll proceed to the next bit. So next bit, I will also set it at 1. I will initially set it at 1. When I set it at 1, the value which I will get is 0.5. This is 0.25. So the new value I get is 1.75. Now my 1.75 is still less than 1.90625. So this has to still be 1. Okay, so this has to still be 1. So this bit will remain at 1. Then I will go to the next bit. So next bit again, I will set it at 1. Okay, I set it at 1. So this corresponds to 0.125. So my new number will be 1.875. Okay, this is my new number. Now this 1.875 is still less than 1.90625. So this bit has to continue to remain 1. Okay. Now I will go to the next bit. This I will add again 1 to it. And 2 raised to minus 4 is 0.0625. So when I add 0.0625 to 1.875, that means 1.875 is 0.0625.
This 0.9375.
Okay. This will be 1.9375. Okay. This is 1.9375. But my value is 1.90625. So when I set this bit as 1, the value is exceeding the original value. What I have to do is I have to give it this bit the value back 0. I will give back the value 0 to it. Okay, so once I give back the value 0 to it, okay, so that means this bit has to be assigned the value 0. Now I will proceed to the next bit. That is 2 raised to minus 5. So next bit, I will give it the value. Yes, yes.
Sir, is the leftmost bit in the fractional part is MSB and the rightmost is LSB, right?
Yes, 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 yes. So that's why I start with those significant bits. Then I go to the lower significant bits. Okay. So now, again, so now I put this as 1. I found the value was exceeding this value. So I put it back as 0. Then I give this a value 1. Okay. Then the next bit, I set the value 1. Then when I put 1 to it, the value which I will get comes out to be
0.65.
2 raised to minus 5 is how much? 2 raised to.
This is 0.03125.
This is 0.03125. Sorry, 0.03125. So the resultant value which I will get is 0.03125. 0.03125 plus we are getting the value, no? So let me just
9065.
Okay. Plus 0.25 plus 0.5 plus 1. Okay, so I'm getting the value 1.90625. Okay, I get the value 1.90625. So that is equal. That is equal to this. So that means this still has to remain 1. I don't do that. And the remaining bits, I will give the value 0. Okay. So what we are doing over here is, I have a decimal value. I want to find the representation in the binary format. I have been given it is Q2.8 format. So I list down those things and I list down 2 raised to 0, all these things I list down. Then I check the sign bit. Okay, it is a positive value. So this has to be 0. Okay. So similarly, this is there. So this is actually, there's a binary, there's a binary search algorithm or something. Or this is similar to your bisection algorithm or your SAR ADC, successive approximation ADC uses this sort of algorithm. Okay. It uses that algorithm for finding out the analog value to digital. And similarly, this is also some sort of analog value which we are converting to digital. Okay. So I hope this part is clear. So then similarly, we have another question. KI is 2.375. So in Q3.7, what format, what it will be then? So that is the same similar question. So that I'll leave it up to you guys to do it. Okay. So now we will start the main thing. Verilog code for digital voltage mode control. Till now, we spend time understanding how Q format works, etc. Now we will go to the Verilog code. So first we will start with the simple voltage mode control. So we have a buck converter. This is my buck converter. And now this is my part. In the gray area, that is my voltage mode control thing. So the ADC is there. It samples the output voltage and generates a signal. That is compared with my V reference signal and that generates my V error signal. Okay. V error signal passes through a PID controller. Okay. And that generates my control value. My control value is compared with my RAM. Okay, this is my RAM. And that generates my reset signal and reset signal, which goes to my SR latch. And the set signal comes from a periodic switching frequency pulse, PWM pulse, and that generates my Q. Okay, my Q, and that signal goes to my high side MOSFET, and it is inverted and goes to my low side MOSFET, etc. Also, with a dead time also is inserted between those two signals. So now, okay. So we have a main module. Okay, we have a module for digital voltage mode control. So it takes the sample value of the ADC. This is my ADC data, which is a 10-bit ADC data. Then also Q plan is there and F clock is there. So these are my inputs to my voltage mode control module. Okay, these are the inputs to this module. The output of the module is this QH, QL, Q load. Okay, Q load is the output, as well as the FADC is another output of this module. So this module generates, takes some input and generates certain output signals. Okay. Now we will go to the overall block diagram of voltage mode control. The output voltage is scaled, okay, by a factor of around 0.27 or something. I don't remember exactly. So if this was 1 volt, this comes out to be 0.27 volt. Then the ADC is there. Okay, the ADC is there, which converts it into a digital value of the form Q1.9 format. Q format Q1.9. My NREF also will be of the form Q1.9. My ME also will be of the form Q1.9. When it passes through my PID controller, it comes out to be of some particular format. I don't remember. We will see in the code. Let us assume it comes out to be of the form Q2.8. Okay, comes out to be form Q2.8. This has to be compared with this thing less than or equal to. So this also has to be of the form Q2.8, suppose. No? Both of these have to be of the same Q format. Then when this value exceeds this value, then it will generate the reset signal. Okay, then this will become 1, and then this Q will become 0. And this is periodically set over here, and after fixed frequency, another pulse comes. So this signal also we must generate. Okay, this signal also we must generate. And this is how we are generating our high side PWM high as well as my low side signal. Okay, there is a sort of dead time is there. Okay, this time is known as my dead time. Okay, all right. So are there any queries in this?
This KF,
Mhm.
KF stands for
It's not very clearly audible. Can you repeat?
what is KF here?
KF is just a feedback gain scaling. Okay, it is like your V feedback is KF multiplied by V output. So my V output is 1 volt and this is 0.27. So my V feedback will come out to be 0.27. That's all. Just a scaling factor.
Okay.
Yeah. So now we will go to the Verilog code. So this is my module. The name is DPWM underscore VMC. It has many inputs, clock, the ADC clock, back, like there's many arguments. Okay, so these are the arguments to my module, to the module which is like a function. So these arguments, some of them are the inputs, like these are the inputs, and these are the output. Okay. So if you see, the clock is the input signal. Clock ADC is output of it. Clock type. We will go through each and everything. So some of them are inputs, some of them are outputs. So now over here, I am defining which are the inputs. So my clock is the input. This Q underscore L underscore R trans. This is for setting which type of transient is occurring. This is this one. My output is the clock of the ADC, clock of the tag, the output, these are my outputs. And Q node also is an output. Okay. These are all, these are scalar values. These are all scalar values because they have only one bit. There's only one bit. But certain inputs are there. That is the input from the ADC. That is 10 bit. So the input to the ADC is a signed value. It is signed to a complement value, and it is from Q1.9. This I must remember that the input ADC data is of the form Q1.9. Okay, but when I define over here, I'll just define it that it is that ADC data. It is a variable of 10, which has 10 bits. When I am running the code, when I am writing the code, I must remember that that it is of the Q1.9. Okay. Similarly, for the DAC data, it is also 12 bit and 12 bit offset binary. Anyway, we are not using the DAC currently for voltage mode control. We don't require a DAC. We require a DAC for current mode control. Okay, this is required for current mode control. So can anyone tell me why we require a DAC in current mode control?
Because current control is an analog at
Yeah.
IL.
Yes.
ILN.
Exactly. Okay. So then, now in the module which we further go through, the module we say some are registers, some as wires. So a register is something which can be only updated, can only change value based on a particular event. Okay, a register can only change its value based on a particular event which is occurring. Okay, but a wire can change its value continuously. Wire can change its value continuously. So similarly, ncon, ne, nout are these variables. This is a PWM signal. That is this signal. Okay, this one. Now my KP, KI, KD, I am giving it as a parameter. As a parameter means it is fixed. It cannot be changed. That is, when I'm executing my code, by chance I put in the code somewhere else, I put KP is to be some other value, something that should not occur. So this is just KP. It is a fixed value assigned to KP or KI, KD, and that will be constant throughout the code. Cannot be updated. Next, we will go to reference voltage.
Sir?
Yes, yes.
Sir, we say when we represent in Q format, it is always in the signed format, right?
Yes, yes. Yeah.
Okay, but they have explicitly returned Q 4.6 signed format.
Oh, these are comments.
Comment line.
Yes, these are comments, so that I remember.
Yeah,
from
comments.
my understanding.
Yeah. No, that is what it is. But say if we write Q of 4.6, it is understood that it is signed format, right?
Yeah, it is understood.
But it is no need to write explicit.
So, yeah.
Okay.
Here, like,
What?
10 episode SB.
Will you repeat?
KP is equal to 10 episode SB.
SP sign bit, not sign bit.
Okay, but 10 is.
This is 001. This underscore is for our own understanding. It is for our own understanding. These are the 4 bits for the integers, and these are the 6 bits for my decimal. Okay.
Here, like, what is KP? KP is, what is the value of KP, sir?
If we see the value of KP consists actually 1.25. 1 and 2 raised to minus 2, so 1.25.
But what is the 10 slash implies? Like 10 apostrophe.
This underscore is just for our understanding, so we know that this is the point.
Apostrophe. Not underscore, apostrophe. Before 10, after 10 and before SB there is.
Oh, this is a prime. That is, this is 10 bits.
Okay.
10
Okay.
bits, and those are sign bits. Okay. That is just the notation.
Okay. Okay, sir. Okay.
So we define constant values for KP, KI, KD. Okay. Then, if you see voltage mode control, it has a V reference. And this is my V output, which comes from my ADC. This is this end reference. Okay, this is my end reference. That is corresponds to V reference. So the reference, I can either give it like, let us say this is my buck converter. Okay, its output voltage is V out is steady state, it is 1. But I want to increase the voltage to, let's say, 1.1. So what I have to do? This NREF, which was this NREF over here, was corresponding to 1 volt. And this delta underscore NREF is like a step of 0.1 volt. So if I want to give it a reference of 1.1 volt, then I have to add this NREF plus delta NREF I have to add, and that will be my new VREF. Okay, that will be my new updated VREF. Okay. So this will be my NREF nominal plus delta NREF will be equal to my NREF. So this is my my NREF nominal corresponds to 1 volt. My delta NREF corresponds to 0.1 volt. And this NREF, it could either be just NREF nominal or it could be NREF plus delta NREF. So we will look into that further. Okay, then what we have to do is we want to capture the output voltage samples. So my ADC, this ADC over here is continuously running. My ADC is continuously running. It is continuously getting trigger signals. And because it is getting trigger signals, it is sampling, it is converting, etc. That is happening continuously. But I don't want to take all the samples. If you remember, we talked about taking only one sample per cycle. Okay, only one sample per cycle. We talked about delay, etc. stuff. So let us just consider we're taking one sample per cycle. So which sample I will take? So the sample which I will take is when this clock comes. When this switching clock comes, that is at the pause edge. So this is my FPWM. Okay, at the positive edge of my FPWM. Okay. When that positive edge comes, I will take the ADC data. And out, I will assign it the value ADC data. Also, what I am doing is my ADC data is of the form Q1.9, but so this is like, it would be like 1.00100 something, etc. It will have, overall, it will have 10 bits. What this command is doing is the last bit, that last bit could either be 1 or it could be either 0. It is ignoring the whatever value of the last bit it could be, and it is giving it a value 0. So if you see over here, it is giving it a value 0. 1 prime B means it is a 1 bit whose value is 0. So my N out, okay, my N out will be this ADC data. ADC data is 1:9. Okay, so 1:9 corresponds to 9 bits. Okay, 9 bits. And sorry, the ADC data 9:1. Okay, 9:1. And it is adding a value 0. Okay. So is this part not clear, or this part? Just tell me again.
Sir, sir, here, in this FSW and FADC are equal, sir, here.
Yeah, over here it is equal, yes. No. Actually, there are two things. No, here they are not equal. You see, if you remember, I have told my ADC. Okay, this is my FADC. Okay, this is coming at a rate of around 25 megahertz. So the ADC is on throughout the time, and it is continuously taking samples, and it is generating outputs. There is a 6-cycle delay. Okay, there's a 6-cycle delay, all that we had told earlier. Okay, now my ADC is so this is my, let us say, this is my time period. Okay, my inductor, or not inductor, the output voltage. Okay, the output voltage is like this. So this is my time period. Okay, my ADC is continuously taking samples. It is continuously taking samples, but
taking samples in 25 megahertz.
at 25 megahertz. Okay, So this is one sample, this is one sample, this is one sample, this is one sample. Now, which sample will I choose for my computation? That depends on FPWM. Okay, this FPWM signal comes over here. So this signal, this sample I will choose for my controlling. But all these samples the ADC is taking. Okay, so the clock to the ADC is this clock. There's one clock here, clock here, clock here, clock here, etc. These are the clocks for the sampling, for sampling of the ADC. So ADC is continuously on, continuously taking samples. But the which sample I am choosing, that is my FPWM. Okay.
And is this FPWM is same as FSW?
Yeah, it is same as FSW. In this case, it is same. Okay. So, okay. So then we will also talk. Also, if you remember, we talk about top-down approach. This, yes. Huh?
Sir, in the digital domain, they are using this N out just to represent, instead of V, they are using N to represent it is digital, right?
Yes, yes. Yeah. So if you remember, we talked about how a module, we cannot define a module inside a module, but we can call or instantiate a module. So that there's a DPWM underscore VMC. PWM underscore VMC. This is our main module. And in that module, we are calling this module, we're calling this module, we're calling the dead time module, etc. All these modules we are calling inside this module. Okay. And these are the arguments which we pass on to it, and we are using this dot notation, which we had explained last week, to pass on the arguments into this module. Okay. So, okay, now one more thing is, why do we give periodic step up and step down transient? This I will show when we see the hardware results. Okay, I will show that way. But okay, let me tell now itself. See, we are doing voltage mode control or current mode control. So what do we want is, we have our output voltage. It is say at around like later 1 volt. Okay. Now, if we apply a reference transient. So reference transient is changing the reference. So it corresponds to 1.1 volt. So this corresponds to 1.1 volt. Okay. So what will happen over here? The output voltage, it will go like this. Okay, it will go like this. Let me change the color. Okay. So the output voltage will change like this, come like this, reduce like this, etc. Okay, so this is how the output voltage will change. This is for my reference transient. This is known as my reference transient. Reference transient. And my inductor current will be like this, like this, like this. It will be going on. There will not be much of a change in the inductor current. Okay. There will not be much of a change in the inductor current. This is my IL. But so this is my output voltage. Okay. Let us now I want to give a load transient. Okay, I want to give a load transient. The current average value of the current I want it to be this much, then I increase it, and then further I reduce it. Okay, so the actual current be my inductor current would be like this, or this form. Okay, it will go like this, go like this, go like this, then it will go like this, go like this, like this. It will be some similar graph like this. Again over here it will reduce and it will come back to this one. So my output voltage, which was over here, it was maintained at say around 1 volt. When the load step came, it will reduce. Okay, and then it will finally come back to its reference value. When the load step down comes, it will increase and then finally come back to its reference value. So this is the thing. There are two types of load transient. There are two types of transient. One is a load transient and one is a reference transient. In the reference transient, I am adjusting the output voltage. I am adjusting the output voltage. And in the load transient, I am maintaining the output voltage, but I'm changing the load current. If I'm changing the load current, what does it mean? I am changing the inductor current. Okay. So these are the two types of transients we give. And why? What we do is when we are running the code, we give a step up. This is like a step up transient, and this is a step down transient. So these are all happening progressively. So there'll be a step up, step down, step up, step down, step up, step down. So this we will continuously keep it to occur. So there are two things you must remember. Why I give these transients is so that I will know whether my control is working. Okay? Whether my control is working. If I want to check if my control is working, see, you could also just give a simple open loop duty ratio and you can get some waveforms. But how will you know that it is working actually? Your actual control is working. So for that, you give these sort of transient, these disturbances you apply. You apply these disturbances and check whether your controller, control loop is able to bring it to the desired performance. That is one thing. Now, why am I giving a repetitive transient? I'm going up and going down, up, down, up, down. Why? Because we will see these waveforms on the oscilloscope. Okay, on the oscilloscope, we will be seeing these waveforms. And these waveforms, see, if you just, then these waveforms should be periodic. Okay, the waveforms which I observe must be periodic. So if you see, let me just actually now. Yeah. So, but here I'm okay, this meeting will end in 1 minute. I'll again start the meeting. Okay. Just one. So there are two cases. Okay, this is my output voltage. This is my reference. So I have to give a period. If I give just one reference and I'm observing this on the oscilloscope, so I must be seeing this to observe it. Okay, and these references are in the order of microseconds. So this thing which will occur, I will not be able to observe it. I will not be able to observe it in the oscilloscope. The oscilloscope may capture and display, but it is too fast for my eye to see it. It is too fast for my naked eye to see it. So what we do, we give a periodic reference command. When there's a periodic reference command, this signal also will be periodic. Here it is not shown in a diagram, but it will be periodic. So when it is periodic, what will happen in the oscilloscope? There is something known as a trigger function. There's something known as a trigger function. And what it will do is this repetitive or periodic waveform, it will hold it as a stationary waveform. To display it as a stationary waveform. Okay, to display it as a stationary waveform. And then we can see this transients are occurring at a very high frequency. But because it is periodic, the oscilloscope, it will be triggered and we can give the what thing will trigger it, which edge will trigger it, at what value of the trigger, etc. Those things we'll have to use an oscilloscope to be able to say it. But we give a repeated signal so that we can view a stationary signal of the oscilloscope. Okay. So any doubts in this?
Sir, how, like, when there is a transient in load, how the output voltage changes, and where there is a change in reference voltage, how it will change? Is there any intuitive explanation for this?
Yeah, yes. Let's see when if you go here. If the load current is increased, that is the inductor current is increased. Okay, because the inductor current has increased, there's the capacitor is there, and this is your load. Okay, This is your IC and this is your I load, and this is actually your inductor, IL. So because your load current has increased, your IL cannot change instantaneously. So your IC will start discharging. When IC starts discharging, the output voltage will fall. It will fall. Okay, that is the reason.
How it is falling, sir? Like, is there consideration of ESR with in
No,
series
no.
with this?
ESR also will come into picture, but the main thing is there's something known as capacitor charge balance. Okay. See, effectively in steady state over here, okay, the how much the capacitor is charging and how much the capacitor is discharging is equal. But in this case, how much the capacitor is charging and how much the capacitor is discharging is different. It is discharging more. Because it is discharging more, that is why the voltage is falling. And from here
Like,
onwards,
how we can say, sir, from which time to which time you are considering it is charging and discharging?
okay, when it is when the voltage is falling, it is a discharging process. That time the amount it is discharged is more than the amount of charge which is stored in it. While when it is starts rising, then the amount of charge which is given in the input is more than the amount of charge which is discharged from the capacitor. And at steady state, the amount of charge stored into it and the amount of charge depleted from it are the same, and so the voltage remains constant. So for this, actually, you have to go through this charge balance concepts and everything. You can go through the previous NPTEL course. There they have taught about it. The derivations also are there.
Okay, okay.
So now we want to create these transient events. Okay, the transient events we want to create. So first is we have a counter. Okay, we have a counter one. Okay, and we have a Qtran is a register, and virus Qtran type. Okay, QLR tran is a switch. It is a switch which could be there at 0 or it could be 1. So if it is at 0, it means I want to apply a load transient. This at 1 means I want to apply a reference transient. So this okay. So suppose it is at position 1, so it is a reference transient. So what will I do is I want it to be this is my FSW, okay? FSW is coming like this, FSW, and that FSW is actually my FPWM, okay? So I have a counter. So for 50 cycles, it will be high. It will be 1. Okay, this will be 1. That is my V reference will be actually my V reference nominal. For the next 50 time, my V reference is equal to V ref nominal plus delta V ref. Okay. So for doing that, I need a counter. So what my counter will do is, this is my counter 1. When the counter 1 is less than n tran by 2, n tran is 100. When the counter 1 is less than 50, what I will do is my Q tran will be 0 and my n reference will be equal to n ref nominal. So this will be equal to 1 volt. Okay. And it will keep on implementing my counter. So this is and this is always at this edge, at this rising edge. At the rising edge only it will go. So whenever the rising edge comes, it will go into this, it will check this condition. If my counter 1 is less than 50, then it will set my Q tran to be 0 and my nref, it will give it a value nref nominal and it will increase the value of the counter. Okay. Next, if so, this is like a counter 1 is an internal thing. Okay, this is my internal counter. My internal counter is there. So, and this is my counter by 2, or this is my n tran by 2. It's over here. Now, if my counter 1 reaches n tran, what does it mean? I have to reset the counter. So I make the counter back to 0. I set my Q transient to 0 and my nref remains at nref nominal. Now, I will consider the case. And so there are 3 conditions. One possibility is the counter has reached this n tran. Another possibility, the counter is less than n tran. So that is when it is less than n tran, it is this condition. Then the remaining condition is when the counter is more than ntran by 2 and it is less than ntran, then it will come over here. In this case, my qtran will be 1 and my nref will be nref plus delta nref. So over here, in this case, over here, vref is 1 volt. Over here, my vref will be 1.1 volt. Over here, my qtran is 0 and over here, my qtran is 1. Okay. So any questions in this part?
Sir, here the event is the when the counter is crossing the reference.
Okay. Here the event is no, there is, let us see that there's a counter, its maximum value is ntran and the minimum value is 0. Okay. Minimum value is 0. When it starts counting, it will increment whenever this edge comes. Okay. Whenever this edge comes, it will increment because it has this always. When this edge comes, then it will go into this block. So the edges come and it goes into the block. So it starts counting. So there's a condition that till this counter value is less than ntran by 2, I will set vref to be its nominal value that corresponds to 1 volt. I will set qtran to be equal to 0. Once it exceeds this ntran by 2 and it is less than ntran, then I will set vref to be 1.1 volt and qtran will be 1. Once it reaches ntran, then it has to be reset back to 0 and then the procedure will continue like that. Okay, it will run like an infinite loop. So that is it clear? Yeah. Now my Q load is given by this formula. Qtran type question 0 Qtran. What does it mean? If my Qtran type is 1, okay, if my Qtran type, this is like a muxing arrangement. Yeah, we are creating periodic transient events. Okay, and you remember Qtran type, if it was Qtran type was 1, that would mean it is a reference. Let us see. Qtran type is 1 means it's a reference transient. Okay, a reference transient. So let us consider for nref. Assume Qtran type is 1. So it will check my nref, which I will give. It will check if depending on Qtran type, if Qtran type is 1, then it will give the value nref temporal. Else, if Qtran type was 0, it will give nref nominal. So let us see my Q load, my nref, okay, and my Qtran type. Suppose my Qtran type is 1, then my Q load will be 0 and 0, and my nref will be, it will be this vref, and then it will be vref plus delta v, okay, 1.1. But if my Qtran type was, and my Q load will be 0, 0, that time I don't want to give load transient. But if my Qtran type is changed to 0, then this will be 0 in this case, and this will be 1 in this case, and this will continue to remain as vref. Okay. So is this clear?
Yes, sir. So
Okay.
so this we have talked this assign Q load statement.
Yeah.
Qtran
Yes.
type question mark 0.
Yeah. So Qtran type will see this. Qtran type is like a mux. It's like a mux. Okay, this is my Qtran type. So it will be 0 or 1. If it is 0, that means I want load transient to occur. Load transient to occur means I want it. This is Qtran type. Okay? Qtran type. If I want load transient to occur means I will give it. Sorry, so this will be Qtran, and this will be Q load, and this will be value 0. So if I want load transients, my Qtran type will be set to 0. Then the signal Qtran will come. The signal Qtran will be assigned to Q load. But if I don't want load transient, then I will give Qtran type to be 1. And if Qtran type is 1, then Q load will always get a value 0. Okay. Okay, so I'll proceed further. Now I want to generate clock. Okay, I want to generate a clock for the ADC. For my ADC, I need a clock and NSW shows me a clock.
Sir?
Yes.
Sir, in the previous slide,
Mhm.
This statement, this assign Q load equal to Qtran type question mark 0 colon Qtran.
Mhm.
Sir, in this Qtran type depends on the value of Qtran, right?
No. That's why these variables are not actual problem. Qtran type is, see, if you see Qtran type is here. This is Qtran type. Where is this? This is Qtran type. Okay. Just like selecting which type
Where,
of
sir?
transient. Here, Qtran type here.
The pointer is not shown.
You can't see it. Now can you see this?
Yes.
So here, this is the Qtran type.
Okay.
So it will be 0 if it's a low transient, it will be 1 for reference transient. I told which are the types of transient we give. We give a low transient or we give a reference transient. So basically,
No, sir, in that statement.
in that statement,
Okay, that is understood, sir.
this is understood. This means Qtran type question. Question means what it will check if Qtran type is 0 or 1. If Qtran type is 0, then I will assign the value of Q load to be the first one. So that will be 0. Instead, if Qtran type was 1, then Q load, I will go to the second one. So Q load will become equal to Qtran. Okay. So what does this signify? If Qtran type was 1, that means I don't want load transient. That means I don't want load transient, then my Q load should always be 0. Okay. So it will be Q load will always be 0. You see over here, Qtran is 0 and Qtran is 1. So it is becoming, it is 0, 1, 0, 1, etc. But I don't want this to be my Q load. In case I don't want load transient, I just want it to be 0. So this statement will select that. This statement will select that. So now, we proceed to clock generation circuit. So we have a clock which is of 100 megahertz. Okay, we want to generate clocks from this. We want to generate this clock. We want to generate this clock. So what we want to do, my switching period, if you see, my switching period will be 100 upon 500. That comes out to be 200 kilohertz. Okay, 200 kilohertz. Okay, this is 100 megahertz. It is 100 megahertz divided by 500. Okay, so it comes out to be 200 kilohertz. Similarly, my FADC is 100 megahertz divided by 4. So that comes out to be 25 megahertz. So my switching PWM, my switching is my PWM frequency. PWM frequency is of 200 kilohertz. My ADC is 25 megahertz. So what actually is happening? Let us see for the ADC part. We have this is my F profile. Okay.
Sir, here we are using 4-cycle delay, right?
Not 4-cycle delay. Just see. So it first checks this. It sees it, it says hi. Then this one it ignores, this one it ignores, this one it ignores. And then it goes to the next one. So that way, basically, I'm doing a division. I'm dividing the frequency. Okay. So for doing this, I need a counter. I will require a counter. So when the first clock comes, my counter will have value 1. Next clock counter will have a value 2. Next clock comes, counter will have a value 3. Next clock comes, counter will have a value 4 and will get reset to 0. And then again, no, it will be from 0, 1, 2, 3. Okay. So when it is, okay, so this is my counter 1, which is my specific frequency clock. This is my counter 2. Let us assume this is my counter 2. It is my counter 2. At this edge it is 0, next edge it is 1, next edge it is 2, next edge it is 3. And again at this edge it again gets reset to 0. So it is a counter which has maximum value 3. This is 0, 1, 2, 3, and again goes back to 0, 1, 2, 3. So this is my counter 2, which is used for generating the clock signals to my ADC. Okay. Is this clear of this part? So
Yes, sir.
it will check whenever the count. So let us see the code. Okay. It checks over here. If my counter 2 is 0, if my counter 2 is 0, means my ADC clock will be 0. It is 0, 1, 2, 3. This is 0, 1, 2, 3. And then it goes back to 0, 0, 1. It is repeating. So it checks. If counter 2 is 0, what will be my ADC clock? My ADC clock will be 0. Then there's a condition if counter 2 is equal to NADC. This is my NADC is my maximum value of 3. If it is that, then this ADC clock should be 1, or else it should be, okay, it should be 1. Okay. But now we are over here. My counter 2 is less than NADC. So it is 1. So it will come over here. It will come over here and it will keep my ADC clock 0. So it'll keep it 0. Again, it checks if counter is less than NADC. Then it will still keep it 0. Then it will come to a condition where counter 2 is equal to NADC. That is here, this condition. And it will go high for that value. Then when it again goes back to 0, it will again go low. Okay, so basically my high frequency switching clock is being converted into a low frequency clock. This is my F clock. This is my ADC clock. This is getting divided by 4. Yeah.
Yes.
So now for the PID controller. So here, like the actual resizing, etc., will be done over here. Okay. So I have defined my NCON to be of 19 bits. Okay. My N proportional time N, it is of 20 bits. All these we will go through. Okay. So what happens is we have this KP into this V error. Okay. KP into V error generates this UP of N. So this KP into N error generates my N proportional temp. My temporary proportional value is KP into N error. Okay. So I get that N proportional temp. Now my KP, if you remember, KP is actually Q4.6. My N error is actually Q1.9. So my N proportional temp will be how much? It will be Q4.15. Okay.
Sir, understood.
Similarly, my N integral temp, my KI, I think, was 1.9. KI is Q1.9. Okay. So my N proportional temp will be Q1.18. It is N integral temp is KI Q1.9 into Q1.9. That comes up to Q1.18. Okay. But these are different. This is Q4.15. This is Q1.18. So what we do over here is, similarly for the derivative, also there is the thing. So this N proportional temp. Okay. Let us see. Okay, actually I made a mistake. that this 4.6 into Q1.9, it will initially come out to be Q5.15. Okay, n proportional temp will be Q5.15. Then we have to do the step that we have to subtract one of the MSBs. First, there will be two sign bits. There will be two sign bits, but now we want to remove one of the sign bits. So what we do is we will just take these main bits. See, n prop temp had 20 bits. Okay, that was actually 19:0. But my n prop, I don't want the extra sign bit. So what I will do is I will take only 18:0. So the first sign bit I am ignoring. Okay, I'm removing it. So my n prop comes out to be like this. And when it, so this was actually my Q5.15 and my n prop comes out to be Q4.15. So this is Q4.15. Similarly, my n integral temp I have converted into Q1.18 and my n derivative is Q4.15. Now we know that my ui of n is ui of n minus 1 plus ki into v error, etc. So that is this part. Okay, that is this part. And then after doing that, we put ui of n minus 1 is equal to ui of n in the iteration. So that is this part. Okay. So next, so this comes out to be of the form my n integral. My n integral is of the form Q1.18, but my n proportional is Q4.15. So my n integral instant, that is my n integral final, I need to make it of the form Q4.15. So what I do is, this is 1.18. I'll have to make it Q4.15. What I will do is, I will add sign. I will do sign extension. I have to add 3 bits. Okay, I have to add 3 bits at the MSB. So I add 1 bit here, 1 bit here, 1 bit here, and those must be the same bits. Then I take these data and I'm ignoring the last 3 bits. The last 3 bits are ignored. So my effectively n integral final will come out to be Q4.15. So,
Sir,
yes, tell.
sir, here is n integral and proportional. Here we are actually adding, no, sir, multiplying, right?
Yeah, yes.
Sorry, adding.
Yeah, we'll have, in the end, we'll have to add it. Yeah, so we are adding over here.
Sir, here if we want to do that, then both the numbers has to be changed, right? Maximum of n and maximum of n.
Okay, understood. So my n proportional was Q4.15. Okay. My n integral was Q1.18. Conventionally, what we will do, what we have shown you till now, was I make this Q4.18. I make this, and I make this also Q4.18, and then I add them. Okay, that was what we used to do. But these last 3 bits are very insignificant. Okay, they're insignificant. They're not necessary. So what Sir has done in his code is, he has, instead of making n prop Q4.15, he made his n integral to be Q4.15. He made it Q4.15, and then he added both of them. So in the integral part, he ignored the last 3 bits because you can ignore it. There's a very, very small, it will be like 2 raised to minus 18, those things. So that you can ignore, right? Such small values. Okay. So those he ignored. So that he did. So that is the code for digital PID control. Then these are the details of the capacitance, etc. This is the power stage parameters. So output voltage is 1 volt, then it's a 1.1 volt, etc. Load can be the 13.5 ohm or it could be 0.33 ohm. Okay. This. And similarly, ADC resolution, DPWM resolution, all this is there. These are the gains. So load transient. So what's happening? The load has shifted up. Normally the load was at this value. So okay. So this is the output voltage. This is my output voltage graph. This is my load current graph, inductor current graph. So in this case, the load current was high, then to step down, we give a command from here to step it down. The command over here to step it up. The command over here to step it down. Okay, this is straight, it will be straight lines. Okay. So when I give the command, what will happen? My inductor current will reduce, it will fall, and my output voltage will increase. And when I give a command to step up, my output voltage will fall and my inductor current will increase. So this is the waveform which you will see in the oscilloscope. And that oscilloscope waveform, you can save it. So you save it in your pen drive and then you can display it. These options are there. Okay. So this is for load step transient. Similarly, there's the step up. They've just zoomed in the part for step up and zoomed in the part for step down, all that. Similarly, the reference transient. In the reference transient, what happened? It was either 1 volt, now it is made to 1.1 volt. Then it is dropped down to 1 volt. Again, it is taken up to 1.1 volt. So this is your reference transient. Okay, this is for your output voltage. And this is your inductor current. Okay, this is the graph of inductor current. Okay, so these are the zoomed in waveforms. So now, is there any other doubt? So I'll be proceeding to current mode control. Okay. I'll proceed to current mode control. So in current mode control, there's a voltage loop is digital and the current loop is an analog. So all the other blocks, these all blocks remain the same. Okay, these all blocks are the same. Only there's a current reference block which is used. There's a DAC is there and this analog comparator is there. And in voltage mode control, this was from PWM, we were getting the reset signal, but now it is from this comparator, give us the PWM signal. At that time, everything all is same. So all those previous blocks remain the same. Only we add a current reference block, we have to use a DAC and we have to use an analog comparator. That is the only change in mixed signal peak current mode control, which we will do in the code. Okay. So this is the main block, etc. So there's a clock generator block, PI controller. In current mode control, we are using PI controller. In voltage mode control, we are using PID controller. So it becomes even simpler thing. Also, we have a current reference and we limit the current. See, we are doing peak current mode control. Advantage of peak current mode control is you can set a peak limit. Okay, peak limit is there. So the inductor current will not cross that peak limit. So those all is possible. So again, we declare the module, etc. that we showed earlier. The same for voltage mode control, etc. These are the same. We are initiating the modules. Okay. The PI controller is used. The code remains the same. As I taught digital PID controller, similarly, the code remains the same over here. The new thing is the current reference generation. Okay. What we are doing is, in this block, we are focusing on this block. All these other blocks we have touched upon. All these blocks we have touched upon. This is the block we have to focus on new. So it is taking two things. IREF is coming from here. GCZ is generating a IREF. And FPWM is this signal. Okay? This is your FPWM switch. This is your FPWM. And NDAC is another thing. So what we are doing is, okay, your NCON signal which was coming here was of the form. Q4.15. Okay, was of the form Q4.15. Now we have to convert that into the form Q is to 4. So Q4.11. We convert into form Q4.11. Just hold on one.
Sir, here are we trying to make the number of bits equal in nmax and ncon nominal?
No, nmax, all this you neglected. No, you just don't consider all this. Okay. This all you don't consider. My ncon, what was my ncon actually? My ncon is this. Okay. This is my ncon. It's Q format on here. Found. Okay. My ncon will be of the form Q4.15. Okay. My ncon will be of the form my ncon is of the form Q4.15. Now I go over here. What's this? My ncon is Q4.15. Now I come over here. So Q4.15 means what? It is 19 bits. Okay, my ncon is 19 bits. What I do is I make it ncon nominal. Ncon nominal is what? I am taking only 18:4. So I am neglecting the last 3, 2, 1, and 0. So I'm making it Q4.11.
You're taking it 15.
So instead of Q4.15 becomes Q4.11. So last 4 bits I am neglecting. Okay. Last 4 bits I am neglecting. So that I've resized it. Basically, I've just resized it. And it will not affect the value much because I'm just ignoring the LSBs. Some of the LSBs I'm neglecting. Then this ncon nominal, I'll compare it with some nmax. Okay, nmax is like some maximum value. I don't want my control ncon to go above this value. Okay. So if I compare it and if my ncon nominal is greater than nmax, then what I do is I assign ndat to be the value nmax. Okay, I assign ndat to have the value nmax. But if it was less than, that, then I give the ndat the value of ncon nominal. Okay. So, and in this case, when I'm giving the value, yes.
We are giving only the 14th bit
Yeah, we're giving
of
only
nominal.
Yes. We are giving only the 14th bit. That is the significant bit we are giving. The signed value we are giving it.
The total we are 15 and MSB minus 1 we are taking care.
Yeah.
We are taking the bit of MSB minus 1.
Yes. The bit of MSB minus 1 and the remaining bits we are giving it. Okay. These bits we are giving it.
So since it is signed, we are taking okay. Since it is signed, we are taking MSB minus 1 here.
Yeah. No. Why we are taking MSB minus 1? So question mark. Yeah, because it will be only positive, right? It will only be positive, it will not have the negative value. So that sign bit is neglected. And you get this ncon nominal.
That's no meaning.
Okay. So you are getting actually your ndat.
No, ndat became 12 bits.
Yeah, it is 12 bits. So it becomes Q1.11. Okay, it becomes Q1.11. And we are inverting the sign actually. This I reference, the main bit, the main MSB bit, we are inverting the sign. MSB bits, okay. This we're converting into two offset binary. Okay. So you see, we have a DAC. No? We are giving the signal to the DAC. This NCON, this NDAC is in 2s complement. It's in 2s complement form. But my DAC, this DAC requires it in offset binary. It requires it in offset binary. So what we have to do, we have to just flip the sign of the MSB. We have to just flip the sign of the MSB. Okay. So the sign of the MSB, we are flipping it, and then we are giving the rest of the bits remain same. That is how I get the value IREF. Okay, the meeting will end in 1 minute. I will again start the meeting and you guys can join. So that is how we have generated IREF. Okay, we have generated IREF. And that will go to my DAC. Okay, it is going to my DAC. Now we have to generate the PWM signal. Okay, for the PWM signal, what do we have is,
Sir, IRF and NP are same. Is it?
this is my the IREF. This is my effective IREF which comes out. Okay. Yes, IREF and NP are same. IREF and NP are same, and then we get a analog value of IREF. Okay, we get an analog value of IREF. This is my analog value. Okay. Then it will be compared with the inductor current. So how actually it works is, okay, this is my switching pulse. Okay, F is W. And over here, this is my IREF. This is my Vsense. Okay, this is my Vsense signal. So once it reaches over here, my Q signal will go to 0. Okay. Goes higher and it goes lower. Okay, this is my Q signal. So earlier we were comparing the with the counter. Now what happens? The set pulse comes from this. This gives me a set pulse. That comes from my clock. See, I told how would you generate a clock for the ADC. I told how you generate a clock for the ADC. But this FSW also you will generate. I told it will be come out to be of 200 kilohertz. Okay. So when that clock comes,
It is some clock by some factor, right, sir?
yes. Then we have actually a 100 megahertz clock. So for ADC, what we did, we divided it by 4. Okay, for ADC, we divided it by 4. But for this FSW, we are dividing it by 500. Okay, so that's why we are getting effectively 200 kilohertz frequency we are getting. So when the clocks, when this switch pulse comes, this will turn on, this will be high. Your inductor current will start rising. When it reaches the peak reference, it will give this reset will become 1 and your Q will go back to 0. Okay, so this is how you are generating your Q signal. Your Q signal will come out. Then, so that is your Q signal. So this is your Q signal. Then if you remember last time we told we have to generate Q high side and Q low side. And we have to insert a suitable dead time. Okay, we have to insert a suitable dead time. So your QPWM, this is your QPWM. Okay, this is your QPWM. Then you have to insert dead time and you have to generate QH. QH will be something like this. Okay. This will be QH. And your QL will be something like this. Okay. This will be your QL. This is your QH and this is your QL with some suitable dead time. Okay. And so this is the code for generating the dead time. So are there any queries in this?
Sir, actually, for generating that dead time,
Mhm.
we have to shift the queue by some
Yeah,
uh,
yeah.
some
This is like
time,
shifting operation.
and
Yes,
then we
yes.
multiply.
And then XOR it on it. Not it.
So here, can you explain this? The shift 6 lines represent that. But sir, can you explain this means how that shifting and multiplying is happened so that we are generating queue?
Okay, suppose this is your PWM. Okay, it gets delayed by some value. Okay, that gets further
Hmm.
delayed by some value. Okay, this is shift 0 or shift 1. Okay, shift 0. Then there will be shift 1, etc. So the signal gets shifted. This is basically shifted slowly by small value. Okay, by a small value, it gets shifted. Over here, we're using POSH clock. So this is like a 10 nanosecond clock. It is coming at a frequency of 10 nanoseconds. So all these are shifted by a value of 10 nanoseconds. Okay.
Hmm.
So now this is your QPWM. So you understood how the shift is happening, right? This QPWM is delayed by
Yeah.
10 nanosecond, then further by 10 nanosecond, etc. It goes on. So my shift 4 would be delayed by 50 nanoseconds. It will be delayed by 50 nanoseconds. Okay. So this will be my QPWM.
60.
Now this will be my PWM delay. This is QPWM. This is PWM delay. And this shift will be 15 nanoseconds. Because we're using shift 4, right?
So now if you multiply QPWM and PWM, you'll get Q high.
Yeah, Q high. You do AND it. Okay, and for this you do or it and NOR. So NOR operation. This is NOR. And this is
Now,
AND. Okay.
since the clock can delay only at the rising side, so one clock is 10 nanoseconds. We are using 6 clock cycles so that we are lighting 6 shift lines.
No, we're shifting 5 times. 5 times.
Okay.
5 times.
Sir, this is parallel, no, sir. This is that non-blocking.
We are non-blocking, so it
We
happens
are using less than or
simultaneously.
equal.
Yes, non-blocking, yes. So it is just like this is actually just a D flip flop. This is just a connection of D flip flops in series. So this is my input Q D. Okay, and this is my clock. Okay, then again another. Sorry, my Q goes to my D, and this is my clock, and this is my Q. It comes back to this D, and clock, and Q. So it's just like a delay register. Like a delay. It's just been delayed. Okay, this is my D flip flops. So depending on the number of D flip flops you connect, that many amount of delay will be there. Okay. This is actually the last time I showed you this one.
Yeah, show this, sir. But this QPWM is assigned to shift 0. Parallelly, shift 0 is assigned to shift 1.
Yes.
Uh,
So okay, let me tell you. So assume initially shift 0, 1, 2, 3, 4, and QPWM are there. This had value, QPWM assume it had value 1, shift 0 at value 1, this at 0, 0, 0, 0. Okay. When you give the next edge, what will happen is QPWM value will come here, so 1 will come here. This shift 0 value will come, so 1 will come here. There will be 0, 0, 0. Okay. This is how it changes. So this value will come here, 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 this value will come here. Okay, like that it will go on. Okay. That way. Instead of swapping it, we are directly just shifting it first. Okay, it will all happen simultaneously.
Okay.
So I'll just quickly go through pulse skipping modulation. in pulse skipping modulation, what do we have is when your reference voltage is less than your output voltage, then you give the PSM signal. Okay, your output voltage is more than your reference voltage, then you give PSM signal. Actually, this graph is not exactly correct. QPSM. Oh, it's at a clock. It's at a clock. Okay, fine. So basically, what you must understand is when the output voltage is greater than your reference voltage, like when the output voltage is less than your reference voltage, then your QPSM is high. Okay. Just with QP, and this QP is a fixed duty ratio. It's a signal of fixed duty ratio. Fixed duty ratio. And QPSM and QP, they are ANDed to generate Q. So the logic is when your output voltage is more, when your output voltage is more than your reference voltage, then you do not need to provide energy. You do not need to provide energy. It's not required. It's not required because your output voltage is more than your reference voltage. So what we do in that case, we give QPSM a value 0, and so Q will be 0. And then no energy will be transferred from your input to your output. But when you find out that your output voltage is reduced than your reference voltage, that means you need to provide energy. So what you need to do is you need to give this pulse. You need to give this signal Q. Okay, Q cannot be 0. You need to turn on and off the switch. In that case, you set QPSM to be 1. And whatever the signal comes here, the same signal will come to Q. So Q is either QP if QPSM is equal to 1. And this happens when your output voltage is less than your reference voltage. And Q is 0 when your QPSM is equal to 0. And this happens when your output voltage is greater than your reference voltage. Okay. So basically the concept is if my output voltage is less, then I need to inject energy. That means I pass a fixed duty ratio signal to my buck converter. But in case my output voltage is more than my reference voltage, then I do not need to add energy. So I do not give my signal to my switch. Okay, so this is the concept of pulse skipping modulation. So these are used for light load techniques. These are for light load conditions. For light load techniques, we use pulse skipping modulation. In digital pulse skipping modulation, what do we have? Just the output voltage, we are taking the samples. We have an ADC which takes the samples, and that is being used for generating the condition, or whether it should be on or off. Okay, you were saying something?
Sir, can the QPSM go less than QP, sir, in terms of time?
Actually, this is not properly correct. Actually, QPSM should be
No, in terms of time,
it should be small. This should not be so big. Actually, it should be small. It should not be so big. The diagram is not correct actually.
Yeah, because then only the Q will be varied. Otherwise,
No,
if
no,
it
no,
is
no,
always
no.
high,
No, no. If Q,
then Q
suppose
will
this,
be equal to QP.
no, yes, Q is equal to QP. Yes, correct, yes.
So what I'm saying is when this QPSM is greater than QP, then always Q will be equal to
No,
QP
no,
only
no.
because we are
Okay,
ANDing.
and I actually one minute. I made an error over here. So it's logic. Wait a minute. Full screen. Let's wait. Okay, it's not able to go to full screen. So can you see this?
Yeah, it is visible, sir. In the slide mode itself, it is visible, sir.
Okay,
No
okay,
problem.
okay. So this is correct. Actually, this is correct. As long as my output voltage is greater than my reference voltage, like unless the clock comes, this cannot change. Okay. So it will hold on to the value. So this value is 1. Okay, this value is 1, let us see. So if this value is 1 and QP is this signal, my Q will come out the same. If my QPSM is 0, then regardless of what QP comes out, Q will be 0. Is that point clear?
Yes.
So now you're asking why QPSM is 1 for so long. Okay, why is it not small? Is that your question?
Yes, sir. Because we our intention here is to, sir, my understanding is our intention here is to not to vary the width of the pulse. We are either having the pulse or we are
Yes.
skipping. We are
Yes.
not varying the width. Okay.
Yes. Okay. So this is my pulse. The effective pulse is Q. Effective pulse is Q. Now, this is just telling the condition whether to skip or not to skip. Okay. So when this is 1, I don't skip. When this is 0, I skip. That is all it is doing. And why it remains on for such a large duration is because
When Q is on, which means V naught, when Q is on, which means V naught is less than V reference.
yes, yes. Yes.
When Q is off, V naught is greater than V.
No. That is for QPSM. That is for QPSM. Okay. See, let us see over here at this point. Over here, this red curve is my V reference. Okay, my red curve is my V reference, and this green curve is my sample voltage. Okay. So when my reference is greater than my sample voltage, my QPSM will be high. Okay, it is high. Now you're saying over here it has become more. Okay, it has become more. But till now, so then this should change. This should become 0. But it is not changed till it comes here. Why is that? Because at this instant only this clock is getting the switching clock. So when this gets the clock, then only this will get updated. Till then it will hold on to the value 1. So once it gets the clock, then it will fall and come to 0. And it will maintain that value. Then now it will check. Now it's saying V output is greater than V reference. So then it will keep the value 0. Okay, it will have the value 0 over here. When the clock comes, it will update the value 0 over here. So since 0 was still there, it will continue remaining 0. Then it comes here. Now V output has become less than V reference. So what value comes to here will be 1. And when it reaches here, then the clock signal comes, and then this gets value 1. So then this comes out to be the value 1. Okay.
Sir?
Yes.
Sir, here the clock, it seems to be the symbol. There is some in the clock written. There is some triangle symbol, which means it is a negative edge trigger clock, right?
This symbol.
Yes, sir. In the Q flip flop, in the beside
D flip flop,
CLQ clock, there is. Sorry. So D flip flop. Besides clock, there is some symbol like a triangle.
No. This is just like positive edge. Positive edge. It's not negative edge trigger. Positive edge. Okay.
There's some memory that okay.
Okay. Yeah. So I mean, I don't exactly recollect. So, but the logic is it should be positive edge. Okay, that is the goal.
Even though it is even though the QPSM needs to change, but it is waiting until the clock.
Yeah, it is waiting until the clock. And see, this is actually required because we just don't want it to randomly change suddenly in between. If it changes, suppose it changes over here. Suppose it becomes 0 off over here, then the pulse will be of this magnitude. But in our desired thing is we want it to be a fixed pulse. We don't want it to randomly vary. Either you give the pulse or you don't give the pulse. But if you're giving the pulse, it should be a fixed magnitude. That's why this QPSM just cannot change arbitrarily whenever the event comes. It is synchronized. Okay, this synchronization is very important. Otherwise, if it is not synchronized, then it will be some random behavior and you will not be able to understand what is happening. Okay. So this one, similarly
for fixed frequency.
Okay. Tell them.
Sir, so for the fixed frequency, we need to make sure that width of the QPSM is greater than QP.
That is being automatically maintained. QPSM is holding its value for time period T. Whatever
Okay.
value is there, it holds
Okay,
it.
because of digital,
Yes, because of the D
digital
flip
control,
flop.
we are having.
Because of D flip flop, it is there.
Okay.
Now, so similarly, this has the various blocks, PSM generation. Okay, the only difference is you have a PSM logic. Okay, rest all are similar. And this is actually a very simple thing. It is either gives a signal or doesn't give the signal. There's no PID controller, nothing is there. Okay. So these are taking the inputs, etc. These all are same. This clocks, ADC clock, switching clock, etc. The same from previous things. Now this is for PSM logic. Okay. So we output is the QH, QL, and we are also giving the the delay, everything is there. Okay. So my QPWM is this. Okay, my QPWM is this fixed frequency pulse width. My QPSM, it is either 1 or 0. Okay, it is either 1 or 0. 1 or 0. And my Q actual signal, oh, my actual, which is my output. Okay, we'll go through the code and we'll understand. So over here, at the positive edge of the F clock or at the positive edge of FPW, then F clock is, if you remember, F clock is at 100 megahertz and FPWM is of 200 kilohertz. When the clock comes and if FPWM, that is FPWM is the start. Okay, it is the start of the period. Then what I will set QPWM to be 0, I will set counter to be 0. Then I will start incrementing my counter. So if my counter is less than my duty, then my QPWM is 1. QPWM is 1. And my counter keeps incrementing. Else my QPWM becomes 0 and my counter still keeps implementing. So this is a simple logic for generating a fixed duty ratio PWM signal. Okay, this is the simple logic for generating a fixed duty ratio PWM signal. But after that signal has been generated, I will see some N error. Okay, N error. It is a and this N error 9 is the MSB, a most significant bit. If how do I get N error? It is actually Vref minus V output. So if my V output is greater than Vref, then my N error will be less than 0. That means it will be negative. Okay. And that means my MSB will be equal to 1. Okay. My MSB will be equal to 1. And in that case, what I want QPSM to be 0. I want QPSM in that case to be 0. So what do we do over here? We will say if N error 9. So this will check if the value of N error is 1. If the value of N error is 1, we will give QPSM to be 0. Else, we will give QPSM to be the value 1. Okay. And this always happens at this edge of FPWM. So it will maintain that 1 or that 0 for that complete time period. Okay. For the complete time period, it will maintain that value. Once it checks QPSM to be 0 or 1, then my Q high side. So my Q high side is simply my QPWM and QPSM. Okay. And my Q low side, I am giving it the value 0. So why we are doing that, if you see this, where's the buck converter? This is my buck converter. Okay, this is my buck converter. So here, actually, this was actually a switch. Okay, it was actually a switch. This is getting QL and this is getting QH. But I'm doing it in diode emulation mode as an asynchronous buck. So I will give QL to be equal to 0 all the time. Okay.
Yeah, understood, sir.
Okay. Yeah, so this is the thing for pulse skipping modulation, and these are some hardware research, etc. shown. So I hope your doubts are cleared. At least you would have got a better understanding of the Verilog code. That Actually, we spend a lot of time on the Q format, multiplication, etc. So that's why I couldn't spend much time on the Verilog code actually today. So apart from that, you have any doubts?
So,
Mhm.
yes, sir. No, we can find out.
Okay, so we'll end for today. So next week, we are going to do about the microcontroller next week. So that will be
Okay.
another different digital platform. Okay. So now we are seeing FPGA, then we will see microcontroller. So please join. Okay. If you have any doubts, you
With this FPGA,
tell her.
no, sir. With this FPGA is ending with this module.
No. The FPGA will be continued further. Just 1 week we will dedicate to microcontroller. 1 week, that is week 9. Then again week 10, 11, 12 is again FPGA. Okay. Yeah. Okay then.
Yes.
Bye.
Good night, sir. Thank you.
Good night. Good night.